Okay guys, in continuation of this unit of random hodgepodge of things, we are taking a step back to derivatives real quick. And the first thing we're going to talk about is derivatives of inverse trig functions. So before we get into the derivative, let's think back to pre-cal for a second and think about our inverse trig functions, okay? So remember we have the basic sine of x graph where it looks like this, okay, from 0 to 2 pi. Okay, goes from up to positive 1 and down to negative 1. This is sine of x. Okay, so let's say that was my function. Sine f of x is equal to sine of x. So the domain of this is from negative to positive infinity, and the range we know is from negative 1 to 1. But if we're looking at this, if I were to continue this all the way in both directions, we recognize that the inverse of this isn't actually a function because it fails the horizontal line test, okay? So what we have to do instead is we have to essentially restrict the domain of my original function, okay? And then if I restrict the domain of my original function, then when I take the inverse, then that would become an actual inverse function. So the domain restriction that we use, okay, so remember normally we have, for the inverse, we just swap our domain and range. So my new domain is going to be from negative 1 to 1, which is perfectly fine. There's nothing wrong with that. But my range can't go from negative to positive infinity, because if I did that, I would have an inverse function that looks like this, and that wouldn't be a function because it would fail the vertical line test. So what I do instead is I just look at my x values of my original curve that don't repeat, so that way I have one continuous piece of all the valid x and y coordinates that I need, so that way I can swap my domain and range in my inverse. That should be inverse of that. And I would have no issues with it being a function. So what we actually do is we extend it back a little bit here to negative pi over 2 and pi over 2, okay? And that's what I'm going to use for the range of my inverse function, okay? So if I were to restrict the domain of my original function from just negative pi over 2 to pi over 2, then I have a nice pretty, like I just essentially want boop, get rid of all that stuff right there. I just want this part of my graph right here, so that way when I reflect it over the line y equals x to create my inverse, then I have a nice function that does not fail the vertical or horizontal line tests. Let's look at cosine. I know that was kind of a quick. So again, your cosine graph looks like this, okay? This is f of x equals cosine of x. I'm going to see if we can come up with a domain restriction here. We know that the range is going to go from negative 1 to 1. So that means our inverse, cosine inverse of x, the domain is going to be from negative 1 to 1. And the range, I need to come up with an appropriate range. So basically, back here, you know, with sine, remember it looks like this, okay? I didn't necessarily want to use this piece, and then I can't use that again because all those y values I've already accounted for. I mean, I do want these y values right here, but essentially by doing that, I would have my domain broken up to this piece and this piece, and that's kind of sloppy. Math people are inherently lazy, so to make it a little bit more efficient, rather than having this piece and this piece over here, what we just said was, okay, well, these y values are exactly the same as the y values back here. So instead of having two separate pieces going from here to here and again from here to here, we just said, okay, let's go from negative pi over 2 to pi over 2, and that's going to, you know, take care of all of the y values that we need. So that's what we did with sine. Cosine works out a little bit easier because if I started at 0, I will account for all of those y values just within pi right here. Okay, so remember this whole thing is graphed from 0 to 2 pi. Okay, but I don't want any repeat y values, because any repeat y values means I fail the horizontal line test, which means my inverse would fail the vertical line test. So I just want these y values right here, so that way I don't have any repeats. So my domain restriction is going to be from 0 to pi, which means my range is just from 0 to pi in my inverse cosine function. Okay, so if we were to look at all of these together, Okay. This is all 6 inverse trig functions. Now this is the actual graph of the inverse trig functions, okay? So if you were to look at the range of your possible values here, negative pi over 2 to pi over 2, 0 to pi, tangent is going to be the same except for the fact that you don't include the endpoints pi over 2 and negative pi over 2, okay? So whenever we're looking at our unit circle, remember when we're getting our answers for like, oh, if I want arc cosine of negative pi over 4, well then I'm going to get, not negative pi over 4, I'm sorry. If I want arc sine of negative 1, my answer would be negative pi over 4 because my answer has to come from negative pi over 2 to positive pi over 2, okay? That would essentially equate to the first quadrant, and the negative of the first quadrant, I mean, technically it's the location of the fourth quadrant on the unit circle, but it's where we're going down to the negatives. So we don't really want to go, we don't want to say the first and fourth quadrant necessarily, but it's the first and like the negative of the fourth quadrant. Let's see, the cosine is going to be from 0 to pi, so that's going to be the first and second quadrants on your unit circle. Tangent's going to be the same as sine, and then arc cosecant, arc secant, and arc cotangent are all going to be a little bit different. We don't focus on those a whole lot, luckily. So I basically, if I know sine, cosine, and tangent, I'm just going to use those and then work backwards to get my arc secant, cosecant, and cotangent. And I'll show those to you as they come up because I know you're like, wait, what? If they come up, and when they do, I'll walk you through those. Okay. So just real quick, let's evaluate each function. So then the arc sine of negative 1/2, basically this is saying what angle or what arc gives me a sine value of negative 1/2. Well, remember, I can only pick from negative pi over 2 to positive pi over 2. So the answer, if I think back to my unit circle, okay, remember I have, from 0 to pi over 2, but then I go backwards to negative pi over 2, okay? So if my sine value is negative, that means I'm somewhere in this quadrant. Well, right here, this would have a sine. This would have a negative 1/2 value. So what angle is this right here? So this would be the angle negative pi over 6 would be the arc sine of negative 1/2, okay? Arc cosine of 0, all right, on my unit circle, where is cosine equal to 0? Again, for cosine, I can only pick answers between 0 and pi. Okay, so then if I wanted the arc cosine of 0, the only angle that gives me a cosine or an x-coordinate of 0 would be pi over 2. So this is just pi over 2. Okay. Arc tangent of root 3. Now tangent's a little bit different because we have to think about the ratio for tangent is that you took the y-coordinate of an angle over the x-coordinate of an angle, and that reduced to root 3. Okay, so on my unit circle, now remember again for tangent, I can only go from negative pi over 2 to positive pi over 2. So I have to go within either this quadrant or this quadrant. Now if two numbers within these two quadrants reduced to a positive root 3, I have to think about what possible combinations do I have. So in order for them to reduce to a positive, well, my x and y are both positive here. My x is positive and my y is negative. So if I reduce those, my y divided by my x would be a negative number. So I don't actually want any angles from down here. So my angle measures have to be from this quadrant. So I've got my three basics here. My coordinates are root 3 over 2, 1/2, root 2 over 2, root 2 over 2, and then 1/2 root 3 over 2. So I need to think about which of these three angles. I mean, of course, we've got, the axes right here, but I hope we recognize that it's not going to be one of those. So in order for my angles my coordinates to reduce to root 3, that means my y divided by my x, y divided by x, y divided by x would have to give me a positive root 3. So if I were to start at my options here, 1/2 divided by root 3 over 2, that's not going to reduce to root 3. That's going to be 1 over root 3, and that won't work. My x's and y's are the same here, so that's going to reduce to a 1. Root 3 over 2 divided by 1/2, that is root 3. Okay, so tangent of some angle, that's what we're trying to find, is root 3. Well, root 3 is root 3 over 2 over 1/2, right? So the only way for me to get that is if I use the angle of pi over 3. So arctan of root 3 is pi over 3. Okay? Arcsine of 0.3, that is not a number that we have easily and readily memorized on our unit circle. So in the event you had this question, if you had a calculator, which you might, you would type this into your calculator and you would round it to 3 decimal places. But since right now we don't have a calculator, we're just going off of exact angles only. We're going to say that the arcsine of 0.3 is arcsine of 0.3. It's some angle measure that its value is the arcsine of 0.3. If we wanted the actual decimal definition, we would type it into our calculator, but we don't have that. Okay, so that's a real quick review of what inverse trig functions are. So now let's take the derivatives of those. Okay, so let's start with y is equal to the sine inverse of x. I want to take the derivative of this, but let's be real here. I have absolutely no idea how to do that. We've never done the derivative of arcsine or inverse sine. Arcsine and inverse sine, those are interchangeable, if you guys didn't remember. But I do know how to take the derivative of sine. We've done that quite a bit. So I'm going to rearrange this. If y is equal to sine inverse of x, well, that means that the sine of y is equal to x. Okay, if I just apply the opposite, or the inverse operation here. Well, I know how to take the derivative of sine, so I can go ahead and take the derivative of both sides. So the derivative of sine is cosine, but I'm taking the derivative of everything with respect to x. So I have to use that special tool from related rates. Remember, we had implicit differentiation. So that means the derivative of sine of y is cosine y dy dx. Okay, remember, y is some function of x. Okay, y was the sine inverse of x. If I knew what the derivative of y was in the first place, I wouldn't have done any of this process. I would have just written it out. But I don't know what it is. So I have to use chain rule and say the derivative of sine of y is cosine, derivative of the outside. But then the derivative of y itself with respect to x, I don't know. So I multiply by dy dx, and I'll see if I can figure out what that is eventually. And then the derivative of x with respect to x is just 1. Okay, so now I've got cosine of y is dy dx equal to 1. So dy dx is equal to 1 over the cosine of y. Well, that's fantastic. So now I know that the derivative of y is, it's 1 over cosine y. It's in terms of y. I need it to be in terms of x because my original function up here was in terms of x. So let's think about if the sine of y is equal to, let's think about what that looks like on a triangle. Because remember, all of trigonometry is the study of triangles, okay? So if I know the sine of an angle, then I can come up with other properties of the triangle itself. So the sine of y is my angle, okay? So the sine of y is x. Sine is the ratio of opposite over your hypotenuse, okay? Remember SOHCAHTOA? So if the sine of y is x, I'm going to go ahead and say like x over 1. So that means my opposite side from y is x, and my hypotenuse, I'll just leave it as 1. Okay? So that way when I take the ratio of my opposite over my hypotenuse, I reduce that to an x. Okay? Well, that's, again, good, but you're like, well, where are we going with this? So I need to find an expression for the cosine of y right here. Well, cosine, remember, cosine of any angle is adjacent over hypotenuse. Well, in this relationship here, if I already know my opposite side and I know my hypotenuse, well, then I can use Pythagorean theorem to find at least an expression for my adjacent side in terms of x. So using Pythagorean theorem, I'm going to have 1 squared minus x squared. It's going to be my adjacent side. Remember, a squared plus b squared equals c squared. So if you have c squared, you got to work backwards. Okay? So then, now if I wanted the cosine of y, okay, that's just going to be dy dx is equal to 1 over cosine of y is equal to the adjacent side over the hypotenuse. So here's my adjacent side. So square root 1 minus x squared over my hypotenuse over 1. Because it's just over 1, I don't necessarily have to write that. So then now I've related cosine of y into terms of x. So I have dy dx all in terms of x. Hey, look at that. Okay? So now what we can say, what we know is that dx of sine inverse of x is equal to 1 over the square root of 1 minus x squared. We just took the derivative of sine inverse. Very cool. Okay? If we wanted to use chain rule here, let's say it wasn't just in terms of x, but let's say you have dx of sine inverse of u. Okay? You're going to do the exact same process except that you have to take the derivative of u. So this is going to be u prime over square root 1 minus u squared. Okay? So that is the derivative of arc sine. Khan Academy has another video explaining this as well. It's very similar, but if there's any confusion on this, I would definitely check that out. Just type in Khan Academy derivatives of an inverse function, but it's probably going to be very similar. Also, Prof. Rob Bob has another explanation as well. Okay? What I want you to do next is I want you to pause the video and try to do the same thing for arc cosine, okay? I'm going to go ahead and work it all the way out real quick. And so then, but I'm not going to like explain all the steps to this one because it's very similar to the last one. So I want you to pause the video, try it on your own, and then just push play and see if you get the same thing that I have. Okay, so hopefully you actually paused the video and now you're back. So this is what I have for arc cosine. You'll notice that it's very similar to arc sine. The only difference in the end is that you have this negative out front. So the negative is the only change. Now remember, sine and cosine are co-functions of each other. Okay, that's a concept that you may have touched on just very briefly in pre-cal last year. They're co-functions of each other. So you'll notice that when we do all of the all of the derivatives of inverse trig functions today, all of the trig functions and their co-functions will just be different. The only difference between them will be this negative right here. Okay, let's go ahead and do arc tan together. Okay, so again, you can pause the video, try it on your own. See if you get the same thing. Y is equal to tangent inverse of x. So the tangent of y is equal to x. The derivative of tangent is secant squared. So secant squared y dy dx is equal to 1. So then dy dx is equal to 1 over secant squared y. Okay. Well, like we did before, I need to draw my triangle here. Okay, so now I'm working with tangent. So the tangent of y, remember tangent is opposite over adjacent. So my opposite side would be x. My adjacent side would be 1. So that means I could use my Pythagorean theorem to find out what my hypotenuse is. And that's just going to be 1 squared. Well, 1 squared is 1 plus x squared. Okay? And I need that. I need this right here because remember secant squared. Well, actually 1 over secant squared, that's the same thing as just cosine squared. So you could write it like that if you wanted to. And the cosine is always 1 over, I'm sorry, not 1 over. Cosine is the adjacent side, okay, the adjacent side over the hypotenuse. So then I would have dy dx is equal to my adjacent side from my angle, which is 1, over my hypotenuse, which is square root of 1 plus x squared. But remember, this is cosine squared, so I'm going to square that. So this becomes 1 over 1 plus x squared. Okay, so that means the derivative of the tangent inverse function is just 1 over 1 plus x squared. If you did it as tangent inverse of u, it's going to be u prime over 1 plus u squared. Okay? Again, we just talked about how co-functions, the only difference would be the negative. So if you were to do this for y is equal to cotangent inverse of x, you would end up with almost the exact same thing. The only catch is you would have a negative out front. So d dx of arc cotangent, or the inverse cotangent, would just be the negative of this. Okay. One more I want to make sure we go over is arc secant. We don't use arc secant and arc cosecant a whole lot. I'll be really straightforward with you guys. Some people use it a lot, some people don't. Our textbook doesn't really rely on it too heavily, but you know, sometimes in college you might see it a little bit more. So we're going to still go over it just to make sure we've seen it before, but just know that it won't pop up a whole lot in our class. So y is equal to, and again, you know, give this a try on your own, see if you can figure it out. And, you know, see if you get the same thing we do. Secant of y is equal to x. Derivative of secant is secant y tangent y dy dx is equal to 1. So that means dy dx is equal to 1 over secant y tangent y. Okay, so now I need to create my triangle to come up with relationships here for secant and tangent. Okay, so y, and I know that the secant of y, okay, so secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So that means secant is hypotenuse over adjacent. So that means my hypotenuse is x and my adjacent is 1. So that means my opposite side must be the square root of x squared minus 1. Okay? Now, one thing that's unique about secant, okay, is if you were to go back to the graphs of arc secant, okay, so if I were to take the derivative of this, arc secant, okay, remember the derivative is the slope of the tangent line. So if I were to draw tangent lines all the way through here, okay, what do you notice about all of these tangent lines, or all of the slopes of my tangent lines? All of them are positive, okay? All of the slopes are always positive. So to account for that, okay, this x-coordinate right here, we're going to put an absolute value around it. Okay, I know that might be a little bit tricky. The book kind of explains that a little bit, but basically the reason for that is because with secant, the derivative of the derivative of arc secant will always be a positive. So we have to make sure that we account for that by having an absolute value here, okay? If that's confusing, just remember you're going to have an absolute value and you're going to call that good. Okay, so then dy dx is equal to 1 over, okay, remember secant is adjacent over, is hypotenuse over adjacent. So hypotenuse over adjacent, so just absolute value of x. And then tangent is opposite over adjacent, opposite over adjacent, so square root of x squared minus 1. So the derivative of secant inverse of x is going to be 1 over absolute value of x, square root x squared minus 1, d dx of secant inverse of u would be u prime over absolute value of u, square root u squared minus 1. Okay? Again, if you did this with arc cosine instead of arc secant, then you would just end up with the negative. But I'm going to show you that all together. Okay? So all together, this is what you've got. Okay? All of this is in terms of u, and so you're using the chain rule for all of these instead of just using them in terms of x. But all of the explanations are on the past couple of pages, so if you need to go back and check those. Now notice, again, arc sine is positive. Arc cosine is the same thing, but it's the negative. Arc tangent, arc cotangent is just negative. Arc secant, arc cosecant. They're opposites of each other. So basically what I would say is if you can memorize these three right here, then you can memorize those as well, just by making sure that they're negative. Okay? So yes, these are things that you want to make sure that you put on that sheet that I gave at the beginning of the year, the stuff you must know cold. These you need to have memorized. I mean, granted, if you don't have them memorized, you can always go back and work them by hand like we just did today. It might take a little while, but you know, hey, to each their own. You do you. I'm not going to judge. Okay, So here is where I normally say work with a partner and give this a try. What I want you to do is go ahead and try these on your own, or if you want to, try them with a partner, and then come back to the video and see if you got the same thing that we did. So assuming you did pause it and you're already back, good job. Now we're going to not pretend, like we're going to say that this represents you. This is you. This is you. And this is you. Okay, so we're going to use all those rules we just had on the last page. So then arc sine is always u prime, so 2 over the square root of 1 minus u squared. So 2x quantity squared. So this simplifies to 2 over square root of 1 minus 4x squared. Okay? Arc tan is u prime over 1 plus u squared. So u prime in this case is 3 over 1 plus 3x quantity squared. So we end up with 3 over 1 plus 9x squared. Okay, everybody following? We're using chain rule. Take the derivative of the outside times the derivative of the inside. Derivative of the outside times the derivative of the inside. Another way to write this, okay, the derivative of the outside, so derivative of arc sine is 1 over square root of 1 minus the inside squared, okay, whatever is inside of this, and then times the derivative of the inside. Well, the derivative of root x is 1/2 x to the negative 1/2, okay? So then if I wanted to clean this up a little bit here, I would bring the 2 and that down, so I'd make that 1 over 2 root x times the square root of 1 minus, well, the square root of x squared cancels out, so that just becomes x. Okay, so I could leave it like this, or if I wanted to, I could clean this up a little bit more. Both of these things are within a radical, so when things are inside the radical, they can be multiplied together. So I can make this 1 over 2 square root of x minus x squared. Either of these answers are perfectly fine. All right, so then arc secant e to the 2x. U is e to the 2x, so the derivative of that is just 2 e to the 2x over absolute value of u, so e to the 2x. Now, luckily here, if I wanted to, I could drop the absolute value because e to the 2x, this is an exponential growth function, it's always positive, unless I had some kind of transformation up front, which I don't have. So this is always positive, so here in a second we can drop that absolute value. And then this is going to be u squared minus 1, u squared, so e to the 2x squared minus 1. So if I wanted to clean this up here, remember these absolute value bars kind of drop away. So I've got 2 e to the 2x over e to the 2x square root. E to the 2x squared is going to become e to the 4x minus 1. Notice these two things will cancel out, so you are left with 2 over square root e to the 4x minus 1. Okay, so if you got any questions, check your book. They might have some explanation, a little bit more explanations of this because these came straight from the textbook. But yeah, that's how you would do those. So let's keep going. Okay, so we're going to kind of take a little bit of a step into natural logs now. So we're going to do some logarithmic differentiation. So we've done logarithmic limits. We did that on the very last set of notes, and I think I may have referenced the fact that we'd already done this in derivatives, and I just realized this morning that's not true. We haven't done that yet in derivatives, and you're about to today. So before we do logarithmic differentiation, you're like, wait, why are we combining all that? We've already done this. I know. Just bear with me here for a second. So remember some basic properties of a natural log function. Okay, the domain is from 0 to infinity, while our range is from negative to positive infinity. Remember, that makes sense because the graph of the natural log of x looks like this. Okay, the function is continuous, increasing, and 1 to 1. Continuous, no holes, no jumps, no gaps or asymptotes. It is always increasing, and 1 to 1. That means it is, you can take the inverse of it. Okay, for every one x, there's only one y. For every one y, there's also only one x. And then the graph is concave down. Ooh, when we say concave down, that means our second derivative would be negative, okay? And kind of going back up here, if it's increasing, that means your derivative would always be positive, okay? Some other properties that are helpful to know for what we're doing up ahead. The natural log of 1 of 0. Hopefully we have drilled that into our brains by now. When I have the natural log of two things multiplied together, I can break those apart by saying the natural log of A plus the natural log of B. The natural log of A to the n is the same thing as just bringing the n out front and saying n times the natural log of A. And then when I have things divided, the natural log of A over B is equal to the natural log of A minus the natural log of B. These are all properties that we learned in Algebra 2 very extensively when you guys did a lot of your expanding and condensing rules. You reviewed them a little bit in pre-cal. Now they're back. Okay, but why? Why are they back? Well, we're going to take those and combine them with what we know about derivatives. Real quick, remember, we've already done these in the past. The derivative of the natural log function. Remember, the derivative of the natural log of x is just 1 over x. Okay, remember x is greater than 0, which fits the domain. And then the derivative of the natural log of u is 1 over u, 1 over the derivative of the inside, times the derivative of the inside, or just u prime over u. This isn't new. This is stuff we've done in the past, okay? But now we're combining this information with the properties that you just saw on the last slide for derivatives, okay? So the reason is because let's say I wanted to differentiate something like the natural log of the square root of x plus 1. Sometimes it's helpful to rewrite the function using log properties before we differentiate. So this function right here, the natural log of the square root of x plus 1, this is the same thing as the natural log of x plus 1 to the 1/2. Okay, and you're thinking, great, that's wonderful. Well, using log properties, I could make this f of x is equal to 1/2 times the natural log of x plus 1. Now I could take the derivative of this very simply. Before, if I want to take the derivative, I have basically a chain within a chain because I have this outside piece and this outside piece that I'd have to account for. Now I can bring that 1/2 out front and this becomes a constant multiple. So then when I take the derivative of this, I have f prime of x is equal to 1/2, just bring the 1/2 down because it's a constant multiple, times 1 over the inside, because remember the derivative of natural log is just 1 over the inside, so 1 over x plus 1 times the derivative of the inside, in this case is just 1. So this basically boils down to f prime of x is equal to 1 over 2x plus 2. That is not too bad at all. What if we had done this without rewriting using our log properties? So in that case, okay, I mean we can do this. So it's f prime of x would be, so the derivative of the natural log is 1 over everything on the inside. So it would be 1 divided by the square root of x plus 1. But then I have to take the derivative of the square root of x plus 1. The derivative of the square root of x plus 1 using chain rule, okay, that's going to be, here, let's do this. Let's go times 1/2 x plus 1 to the negative 1/2, okay, and then times the derivative of x plus 1, which would be a 1. Okay, again, it's doable. It's not that pretty, but it is what it is. So let's see if we can clean this up a little bit. And so I've got 1 over, let's see, so I've got this 2. I'm going to bring that out front. 2 root x plus 1. Well, and this is x plus 1 to the negative 1/2, so that also gets bumped down to the bottom. Okay, and then times 1. So then now I have these two square roots. Well, these are the same thing, so 1 over 2 times x plus 1 equals 1 over 2x plus 2. So you end up with the exact same thing. This question, you know, it wasn't too many more steps to do it one way or the other. Others are going to be a little bit more complicated, as you see overall, but it's just something that you can try to do by rewriting first before you take the derivative. I feel like this would require less steps and less opportunity for mistakes than the chain rule within the chain rule, so on and so forth. But it's up to you. I want you to pause the video, attempt this one, Okay, using your log properties. I mean, this is going to be quite a few log properties all in one here, but then come back and see if you get the same thing. So I've got f of x is equal to the natural log of this rational. Well, when I have two things being divided within a natural log, we can break that apart using subtraction. So I'm going to say this becomes f of x is equal to the natural log of x times x squared plus, x squared plus 1 squared minus the natural log. I'm going to go ahead, and this is under a radical, I'm going to go ahead and write that as 2x cubed minus 1 to the 1/2. Now, I am not even going to attempt this using the other method of not rewriting first, because this is going to be the nastiest quotient rule with chain rule on, not the nastiest, but gross enough that I don't know. If you want to do that, you knock yourself out and have a good time. I'm going to pass. Okay, so now I've got these, okay, within this natural log, these two things are multiplied, and within this natural log, I have this exponent. So I'm going to break this one up first. So I've got f of x is natural log of x plus the natural log of x squared plus 1 squared minus, bring the 1/2 natural log of 2x cubed minus 1. Let me see if there's anything else I can do. Yeah, I have one more. This one is good. This one also has an exponent, so I'm going to bring that one out as well. So natural log of x plus 2 natural log of x squared plus 1 minus 1/2 natural log of 2x cubed minus 1. Okay, I don't think I can expand that any further. I think that looks pretty good. So now let's go ahead and take the derivative. Derivative natural log is 1 over x plus 2 times 1 over x squared plus 1 times the derivative of the inside, so that's 2x, and then minus 1/2 times 1 over 2x cubed minus 1 times the derivative of the inside, which would be 6x squared. Okay, so then now I just want to see if I can simplify this a little bit, probably not too much more. And I'm going to have the derivative is equal to 1 over x plus 2x, so 4x over x squared plus 1 minus, let's see, this 1/2 can reduce with that 6 to make that a 3, so 3x squared over 2x cubed minus 1. So that one, honestly, in the end, didn't end up being too bad, but if you had tried to do this originally, oh gosh, you'd have to use quotient rule and chain rule within that quotient rule. That would be a big nasty mess. It would eventually work out and you could somehow simplify it down to this. It just probably wouldn't look quite the same, and it might take you, quite a bit longer to do. Okay? Now, what if you had this scenario? Now, what if I'm asking you to find the derivative of this, and it's written as a fraction. Now, technically, this is a quotient rule scenario. Okay, so if you wanted to, you could use the quotient rule, and you can use the chain rule within that quotient rule. By all means, knock yourself out. But the reason why we're doing this all in part of this video is so that way we can recognize that we could rewrite this as a natural log problem and use our natural log properties before we take the derivative. I know what you're thinking. You're like, there's not a natural log here, Miss Murphin. What are you talking about? So what we do is we basically put it there. But what I do to one side, I have to make sure that I do to the other side. So I'm going to go ahead and just take the natural log both sides. So natural log of y is equal to the natural log of x minus 2 squared over square root of x squared plus 1. Hey, now I have a natural log. Okay, well, where do we go from there? I understand. So now I'm going to use that natural log to rewrite this whole thing before I take the derivative. Okay, so the natural log of y is equal to the natural log of x minus 2 squared minus the natural log of x squared plus 1 to the 1/2. Both of these have an exponent, so I'm going to bring those out front for each one. So 2 natural log of x minus 2 minus 1/2 natural log of x squared plus 1. Okay? Is there any other log property that I could apply? No, I don't think so. Okay, so let's just take the derivative. Well, the derivative of the natural log of y, again, I'm taking the derivative of everything with respect to x. So that means I have to use implicit differentiation here. So I'm going to have 1 over y dy dx. Remember, dy dx is what we're looking for. The whole goal is to find the derivative of y with respect to x. So this is what we are trying to find. 2 times 1 over x minus 2 times the derivative of the inside, which in this case is just 1, minus 1/2 times 1 over x squared plus 1 times 2x. Let's see if we can clean that up a little bit. So 1 over y dy dx is equal to 2 over x minus 2. Those two cancel out, so I have minus x over x squared plus 1. Okay, and then now I'm close, but no, not quite. I need to isolate this. So to isolate this, I need to get rid of this. I'm going to multiply both sides by y. So dy dx is equal to 2 over x minus 2 minus x over x squared plus 1 times y. Well, okay, but what do we do with the y? Well, I already know what y is. Y is what we started with. X minus 2 squared over the square root of x squared plus 1. So then dy dx is going to be 2 over x minus 2 minus x over x squared plus 1 times my original y, x minus 2 squared over the square root of x squared plus 1. Ta-da! Again, if you had gone up to the original question up here and done this using the quotient rule, you would eventually have gotten something very similar. It might look slightly different because of how you have it simplified, but you get the exact same thing. So if you have a really nasty quotient rule situation, this is a way of telling you, like, hey, maybe not try the quotient rule, maybe try taking the log of both sides and see if you can use those properties instead. Okay, let's see what else we got. Oh, derivative involving absolute value. Okay, so if u is a differentiable function of x such that u is not equal to 0, then the derivative of the natural log of u is equal to u prime over u. Wait a minute. Where'd the absolute value go? Okay, well, and again, why do we take the absolute value of log right here? I'm sorry, not the absolute value. Why do we take the absolute value of u? Well, basically, you can't take the log of a negative number. So if your expression for u ended up being a negative term, we needed to make sure that we take the absolute value of it before we plug it into the natural log. So that's why we do that. Now, why is it when we take the derivative that the absolute value just goes away? Well, here you go. So whenever we solve absolute value functions, remember, like if the absolute value of x is 5, well, that means x is either equal to 5 or negative 5, okay? Well, so if u was greater than 0, then the absolute value of u is the same thing as u. And then it says theorem 5.3, that's what this theorem is. If u is less than 0, well, then the absolute value of u would actually be negative u, because you are finding the opposite, okay? Because u would have been a negative, and you take the absolute value, makes it positive. Okay, so you take the derivative of the natural log of u, and remember, in this situation right here, u is like the term u itself is a negative, okay? So then in order to make, like when you take the absolute value of it, to make it positive, you would need to like multiply by a negative, okay? So the derivative of the natural log of absolute value of u is the same thing as the derivative of just negative, of natural log of negative u, which would be a positive expression, okay? Well, then the derivative of the natural log is just u prime, so negative u prime over u, because remember your negative would be your like your constant multiple. Well, then the negatives would just cancel each other out, so you end up with the exact same thing that you had before. So this is a really long-winded way of saying if you take the derivative of the natural log of the absolute value of something, hey, the absolute value just basically goes away. Cool? Cool. Okay, so then if I wanted to take the derivative of the natural log of the absolute value of cosine x, then I take the derivative first of, natural log. So f prime of x is 1 over the inside cosine of x, ignoring the absolute value, times the derivative of the inside, negative sine of x. So f prime of x becomes negative sine over cosine, which is just negative tangent of x. Okay, let's look at one more. Okay, so then let's bring everything together that we've done today so far. So I want to find the relative extrema of y equals the natural log of x squared plus 2x plus 3. Okay, well, when we want to find relative extrema, remember we need to look for our critical numbers, and we find critical numbers using our derivative. So let's start with that. Let's find critical numbers. So y prime is equal to 1 over, keep the inside the same, so I've got x squared plus 2x plus 3 times the derivative of that inside, so 2x plus 2, so y prime is equal to 2x plus 2 over x squared plus 2x plus 3. So to find my critical numbers, I need to set this whole thing equal to 0 first, so 0 plus 2x plus 2, so negative 2 is equal to 2x, so x is negative 1. So when x is equal to negative 1, I have a 0 in my numerator. Okay. I also need to find out where the denominator is equal to 0, or so I can find out where my where it's undefined. Y prime undefined. X squared plus 2x plus 3. I don't think that will, I mean, it definitely doesn't factor. If I wanted to check to make sure if I had a real solution, I plug it into the discriminant of my quadratic formula. So I would have b squared, so 2 squared minus 4 times 1 times 3. This is going to end up being a negative number on the inside, so that means I have no solutions here. So there's not a place where my derivative is undefined. Okay, cool. So then x equals negative 1 is my only critical number, and I'm just trying to find the relative extrema. So let's just plug this into our chart here for first derivative test. So I'm going to go from negative infinity to negative 1. What's happening at negative 1? Negative 1 to infinity. At negative 1, I know that my derivative is equal to 0. So then if I plugged in f prime of negative 2, and over here I'll plug in f prime of 0. Anytime I can plug in a 0, we can, because it just makes life so much easier. Because if I have 0, I have positive 2 up top and then positive 3, so that's going to be a positive. Okay, and then if I plug in a negative 2 on this one, so 2 times negative 2 is negative 4 plus 2. So it's going to be a negative 2 up top. So I have a negative in the top, and then negative 2 squared is positive 4, but then plus 2 times negative 2. So that cancels out, plus 3, so that's a positive. So negative divided by positive is a negative. Okay, so my first derivative changes from negative to positive at x equals negative 1. So then I need to determine the location of that, meaning I need the y value. So what is y of negative 1? So natural log of negative 1 squared plus 2 times negative 1 plus 3. So that's going to be the natural log of 1 minus 2 plus 3. 1 minus 2 is negative 1 plus 3 is positive 2. So natural log of 2. So y has a relative minimum at the point negative 1 comma natural log of 2, because y prime of negative 1 equals 0, and y prime changes from negative to positive. If it had changed from positive to negative, it would have been a relative maximum. Okay, so natural logs, derivatives of inverse functions, all that combined in one awesome video. Hope it all makes sense. As always, Khan Academy, Prof. Rob Bob, your textbook. This is coming from sections 2.4 and 2.6 in your textbook if you have any questions. I will post the filled in version of the notes on Canvas as well. So yeah, there you go.